All good things. So I was given very, very loose instructions, which I will take advantage of. I was asked to talk about various aspects of dark matter. Of course, one thing that's very nice about this school is that there are a lot of lectures about dark matter. And so you'll be getting a lot of information from Mike Dine about the axion. Reuven Essig will be talking about news searches. Peter Graham will be talking about very, very light types of dark matters and searches for them. So I'm going to try and set things up and give you sort of an overview of what kind of things go into model building for dark matter and some of the ingredients that people have started using with these days. Now, I can't assume that everybody in here has taken a cosmology class, and it's a very important thing to have a rudimentary working knowledge of cosmology to talk about dark matter, because one of the critical things about dark matter is where it came from, how it got to be where it is now, and all those things. So let me begin. I'm going to start these lectures just by giving us a lightning review of cosmology. If you want to do precision calculations, of course, you need better results than I'm going to give here, but at least for the qualitative understanding of the ideas that I want to talk about, I'll try to make this all self-contained. So, the first thing to know about the universe is that it is a homogeneous, isotropic universe, at least so far. Right? So you'll know this, homogeneous and isotropic. And in general relativity, you categorize and understand the universes by use of a metric. So you measure distances in the universe with some metric that takes you from your coordinate system into some distances. And because the universe is homogeneous and isotropic, the metric that we have that can be describing this is the following, where you write a space-time interval, ds squared is minus dt squared plus a squared of t dx cubed. So this isotropy is represented here, that you can rotate this dx cubed in any direction you want, and homogeneous in that there's no special coordinate anywhere in this universe. And the only way in which this metric evolves is that there's this scale factor a out front, which describes distances. So how do you think about that? The way you think about that is that you go into some time of the universe t1, and you draw some box here, and then as the universe expands, that box will expand uniformly in every direction. So this length will stretch out, this length will stretch out, and this length will stretch out. So you'll go from this box to this box. And so the entire expansion of the universe can just be described by a scale factor which is changing with time. Okay? And that is the critical thing to understand about the Friedmann-Robertson-Walker cosmology, is that forgetting about the fact that there are galaxies and galaxy clusters, a leading order of the universe is totally smooth and isotropic, and you can describe everything that's going on by a single function of time, a of t, which describes how the universe is expanding. Obviously, since we have plenty of time, even though we have a discussion section tomorrow, please don't hesitate to interrupt, shout out, whatever you like. My handwriting is terrible. Please tell me if you can't read something, and I'll correct it. So what I wrote there is this quantity h is the Hubble parameter. And the Hubble parameter, which is the logarithmic derivative of a, or the derivative of log of a with respect to time, is the quantity which is probably the most useful in characterizing what is interesting or not interesting in the universe. And there are multiple ways of thinking about h. And so let me just write down what they are, because if you talk to an astronomer, how they think intuitively about h is very different from how a particle physicist will think about h. So for an astronomer, h is a distance velocity relationship, right? So that is to say that if you measure a distant galaxy and you see how far away it is, and you measure how fast it's receding from you, at least for the nearby universe, those two quantities are proportional to each other, and that is codified as Hubble's law, which is where this comes from. But that's not actually the most useful way of thinking about this, because even though you can write h as some quantity of kilometers per second per megaparsec, fundamentally, the Hubble constant is a rate. It's an inverse time quantity. And so the way you should think about this also is that h is a time scale over which the universe changes qualitatively by order 1. Now, that precise order 1 factor will be different whether we're talking about the early universe or the middle universe or the late universe, but it's always, for everything, all the times that I'm going to be interested in, it's always going to be some order 1 factor. And so what that means is that you calculate the Hubble constant, or Hubble parameter. It's not actually a constant. You calculate the Hubble parameter, and the corresponding time scale tells you the time over which, say, the universe will double its length scale, more or less. So that box will go to that box in 1 Hubble time. Okay? And lastly, h is a distance scale. I mean, we're all relativists here, so distances and time scales are the same thing. But it is also a distance scale which is effectively the horizon size of the universe. So this is effectively the size of the universe. Now, again, there's an order 1 constant out front of this that dictates what precisely I mean. But since h inverse is the time scale over which the universe changes by order 1, it is also effectively approximately the amount of time the universe has been around. And so it is effectively also, multiplying that by the speed of light, how big the universe is currently. Okay? So it is how far an observer starting back in the Big Bang, forgetting about inflation for the moment, starting back in the causally connected Big Bang, can watch out and see a signal propagate. So currently we have a universe, our current Hubble rate is approximately 10 billion years inverse, and that's about how far we can see, up to order 1 factors. And these are 3 very, very different ways of talking about the Hubble constant, and they're all very, very important. This one is, of course, very important for astronomy. This one is going to be important for talking about equilibrium processes, and this one is going to be important for talking about observed properties and structure of the universe. Questions about this so far? So, in a flat universe, we have the Friedmann equation, which is that the Hubble constant is 8 pi over 3 Newton's constant times rho, where rho is the energy density of the universe. So that is to say that rho is equal to rho matter. So that includes dark matter, atoms, gas of all kinds, radiation, where radiation could be neutrinos, can be photons, and any other sorts of mysterious radiation, cosmological constant or dark energy, the energy density that is associated with space itself, and so on. Anything else? And G Newton is Hubble, the Planck mass to the minus 2, which is approximately 10 to the 19 GeV, as you know. So why does this matter? This matters because this means that we can understand how fast the universe is changing by understanding what is in it. So when we talk about the cosmology of the universe, we're going to talk about the different eras of the universe when the universe is dominated by the cosmological constant, or dominated by radiation, or dominated by matter. And these things are going to tell us how fast the universe is and what the appropriate timescales are. So For a given rho, given energy density rho, we characterize that rho by an equation of state parameter W. And that W is approximately the relationship between the pressure and its energy density. So it's not my choice to have had a P and a rho be so close to each other and come up in cosmology as much as they do, but that's how it is. So for any given fluid rho, or any different energy density rho, there's some equation of state parameter that relates to the pressure. Yes?
Why do you call that an approximate relation? I thought that was the definition of W, but that's how I always thought.
Because really what it is it's d rho by dp properly, which usually has this simple expression, but not always. And you have situations where, of course, you can have situations where a given fluid on certain distance scales has a simple relationship like this, and in other distance scales has an additional pressure that comes from the fact that you've got some quantum pressure or something like this. So for all of our purposes, it's like this, but I have to say that this is not exact, because if you take this as exact, you might go off and do something dangerous. Right. So we describe a fluid by its equation of state parameter. So you can look at the equation of state parameters of the different fluids. And again, up to this approximation, a fluid will dilute in a fashion that is dictated by its equation of state parameter. So if I start with a given energy density and I let the universe expand, that energy is going to dilute, and you can tell how it dilutes by categorizing it with this equation of state parameter. So for instance, the cosmological constant has an equation of state parameter -1, so it's constant. Dark matter has an equation of state, cold dark matter has an equation of state parameter 0, so its energy density dilutes like a to the -3, and radiation has an equation of state parameter of 1/3, so its energy density dilutes like a to the -4. And all of these things make intuitive sense, and I'm just asserting these, you can derive them, but they make intuitive sense because the cosmological constant is energy density associated with space, so as the universe expands, obviously you still have space, so that energy density hasn't diluted. Dark matter, you start with your box full of stuff. As you expand the box, you have the same amount of stuff in just a bigger box. So A cubed is like a volume. So this is saying that the energy density in dark matter dilutes like volume. And radiation, well, if I have a bunch of photons in a box, as I expand that box, of course, the number of photons will dilute like a to the -3. But each individual photon, you can think of it as stretching out to a longer wavelength. So the energy in any individual photon will also redshift like 1/A. So the energy of a photon redshifts like 1/A, and the number density of photons redshifts like a cubed. So altogether, you get a to the -4. So, good. So, what can we do with that? Well, you can ask questions about what does the energy density in various types of fluids look like. Well, the energy density in radiation goes like t to the 4th. So this is kind of obvious. Energy density is energy per unit volume. Volume has units of energy cubed. So the units of energy density is energy to the 4th. If you're in a relativistic universe where you have no other units, the only unit you have is temperature. So radiation energy density has to scale like t to the 4th. Just dimensional analysis alone tells you that. There's a factor of G, which tells you how many different degrees of freedom you have in your radiation fluids, spin states, flavor counting. And then there's a factor that relates to whether it's a fermion or boson. But for the most part, when people do these approximate calculations, you'll just say radiation density goes like T to the fourth and be done with it. Certainly I will for today. For non-relativistic matter, it's, of course, just the number density of the individual particle, which I'm labeling here chi, times the mass of that particle chi. And an equilibrium particle, if you have a particle which is in equilibrium, then the number density can be written like this. Again, you've got some dimensionful parameters out front. You no longer just have temperature, so the mass comes into play in setting the scale. But of course, the most important factor in determining the amount of an equilibrium non-relativistic species is this exponential, the Boltzmann suppression, which goes like e to the minus m over t with a chemical potential that can correct that. So if you have some residual baryon number density or lepton number density or something like that. But neglecting the chemical potential for a moment, the number density goes like the characteristic energy scales times e to the minus m over t. And that's, of course, just the usual Boltzmann factor that when you get to low temperatures, it's very easy for particles to convert into energy, but it's very rare to have a process that has enough energy to go back the other way. So, we're almost done with our lightning review. So, the temperature of a fluid, of a relativistic fluid, will scale like the scale factor, 1 over the scale factor, assuming that there is no entropy production So assuming I just take a single fluid and I let the universe expand with it, that the energy density of the temperature of that fluid is going to go like 1 over A. And the way you can think about that is that every photon, again, has its momentum, and as the universe expands, that momentum gets stretched out, so all the energies in that fluid get redshifted like 1 over A. So why is this useful? This means that as the universe expands, the temperature drops. So for the most part, we can use the temperature as a time variable. Properly, we're using T inverse as a time variable. So the universe starts out at a very, very high temperature, and as the universe evolves, it goes to lower and lower and lower temperatures. So T inverse is increasing as you go forward. And if you forget about entropy production and a few hiccups along the way, that's a very, very good clock to use to keep track of the universe. So during the early universe, the Hubble constant squared I know you can't read some of that, but that's okay because almost none of it matters. Except for this final scaling, which is that I can take the Friedmann equation that I had before. I assume that I've got some relativistic fluid in the early universe. I have some number of degrees of freedom G star that's summing up all of my different fermions and bosons. And I plug it all in. You factor things. And what do you get? You get that the Hubble constant is approximately equal to T squared over M Planck. times the degrees of freedom to the 1/2. And the number of degrees of freedom in the standard model can go up to slightly more than 100. So G star to the 1/2 can, by ignoring it, can give you an error which is approximately a factor of 10. But for the most part, when you're doing just order of magnitude estimates in the early universe, that's fine. So h equal to t squared over m Planck is usually a pretty good approximation. Questions? Great. Okay. So that is the early universe. So you can draw a plot of energy density versus time, and you can look at the different components of the universe, and you can look at how they evolve. So if you go way back in time, the dominant component of energy density was radiation. It drops like t to the -4. Then you have cold matter, non-relativistic matter. It scales like t to the -3 because it's diluting like scale factor, and scale factor is, t to the 4, t to the 3. It's scaling like t to the 3. And then you have dark energy, which is constant. And you have these critical moments in the history of the universe. We're about here. So we've only recently had this transition where dark matter got overtaken by dark energy. But there's this earlier period here, which is what we refer to as the temperature of matter radiation equality. That comes at a scale factor of about 3,300, or 1 over 3,300 for A, and a temperature of approximately 1 electron volt. Okay. So if you go to temperatures, by which I mean the photon temperatures of the universe, you go out, you look around you, there's the CMB. I can take that CMB, I can go back in time and ask what its temperature was. And if I go back to the time where the temperature of that CMB was 1 electron volt, prior to that time, the universe was dominated by radiation, and after that time, the universe is dominated by cold matter. So that means that the Hubble constant in the early time period is going like t squared, and in this period of time, the Hubble constant is going like t to the 3/2. So that's all homogeneous. That's just a smooth universe expanding, and this is the quantities that dictate for us how fast it's expanding, and that we can use to compare with other timescales. Questions about this? Okay. Then the last thing that I will do in the lightning review of cosmology, almost, is to make one deviation from the smooth universe to say that the universe is not smooth. But it's characterized by perturbations which we call delta, which is the deviation from the average energy density divided by the average energy density. Yes?
That temperature 1 eV, that's in the same ballpark as the recombination temperature.
That's right. It's an accident. It's an accident. So that's a very good point, and we'll come back to that in a little bit. So recombination happens at a temperature of about 0.3 eV at a redshift of between about around 1200, and it's for our purposes and for the fact that they're so close together is just an accident. Maybe there's some deep underlying anthropic reason for it that I will not be getting into, but from our point of view, it's an accident. But it's a very important accident because the fact that there was a period of time before recombination when the universe was dominated by cold matter is very important, and we'll mention that in just a minute. But for our purposes, this is just an accident. So what he's saying, which is a good point, not to scale, is that right here, if this is 1 electron volt, then here at 0.3 electron volts, you have a process by which electrons and protons go together and form neutral hydrogen. And when they form neutral hydrogen, that's the redshift at which we observe the cosmic microwave background. Okay, so the universe is characterized by perturbations, delta rho over rho. So rho is the average energy density of a given fluid at any given time, and delta rho is the perturbation from that. And what we observe is that there are primordial perturbations in all fluids that we've observed at all scales, and that they are scale invariant. So that when you normalize this in a scale invariant fashion, the size of fluctuations you see on 1 gigaparsec scale are the same as the size of the fluctuations that you see on 1 megaparsec scale. At least the initial perturbations were the same. Now, that's not exactly right. There's a slight running of the power as you go to smaller scales, but it's very, very close to a scale invariant spectrum. And if you are in a radiation-dominated universe, then the energy density in dark matter, in a cold matter fluid, will grow like the log of A, while as in matter domination, delta will grow proportional to A. I'm not trying to get very technical about this point, but all I mean is that if you start in a universe that has a little bit of extra matter in some place, gravitationally that will draw stuff into it, and as it draws into it, that overdensity will tend to grow. During radiation domination, those overdensities grow very, very slowly. During matter domination, those overdensities grow much faster. And that's going to be very important. Okay. Last point on cosmology, which is not even about cosmology, it's really just about thermodynamics. As I said, the way we think about the Hubble parameter is it is a time scale, and it is a time scale that characterizes both how long the universe has been around and how fast it's changing. So it becomes the figure of merit for comparing any other quantity that you have. Yes?
What mechanism is behind the course of radiation perturbation?
Sorry, say that again?
Why perturbation of radiation?
Oh, these are perturbations of dark matter. These are perturbations of only cold matter are growing like this during radiation domination. So during the universe, when you have radiation domination, dark matter perturbations will grow like this. But the radiation perturbations are not going to grow. They will oscillate as they do as a pressure fluid. So then the perturbations will actually stop growing. So the critical comparison is if you have some process characterized by a rate gamma, then you have the question, is gamma bigger or less than the Hubble rate? And you can imagine a process, for instance, a neutrino and an antineutrino annihilating into E plus E minus in the early universe. And you can ask the question, is this process in equilibrium or is it not in equilibrium? So to figure out whether this is an equilibrium process, you would do the following. You would say, well, I'll look at the number density of neutrinos. So I imagine I'm this neutrino. I'm flying through the universe. I'm going to scatter on some background neutrino. So that's proportional to the number density of neutrinos, with some cross-section times velocity sigma v. And this whole thing, since this has to be a Z boson here, is ultimately proportional to G Fermi squared. And then since I'm in a relativistic environment, then the only way that I get my dimensions right is by putting a t to the fifth here. So overall, the rate for neutrinos going through a Z boson into E plus E minus, you can estimate as just being G Fermi squared t to the fifth. And you want to compare that to to the Hubble constant, which is T squared over m Planck. And the critical point is that because they have different powers of T, this process is going to be very, very big in the early universe, and then as time goes on, it's going to get smaller and smaller and smaller, till eventually this takes over. So you can set these two things equal. And find the temperature at which this transition happens. And you find that it is around the MeV scale. So this is the kind of, I'm just sketching this out because this is a process that we know happens in the real universe, that happens with the particles in the standard model, which is you ask a question, are neutrinos in equilibrium with the electromagnetic background? So photons can be in equilibrium with electrons, and electrons can be in equilibrium with neutrinos. So when did that happen? Well, what this tells you is that if you go to temperatures above an MeV, then the neutrino annihilation rate into electrons will be higher than the Hubble rate. So that means that there'll be at least one annihilation in every Hubble time. So on average, a neutrino will not last a whole Hubble time before it annihilates. So that will tell you this is an equilibrium process. I'm not trying to dwell on this too much except to say this is the kind of process, this kind of calculation that one does quite a bit of, and just checking to say, is this an equilibrium process or not? You estimate the process, you compare it to the Hubble rate, and see whether it's larger and for what parameters. I should add that there are multiple types of equilibrium. There's, of course, chemical equilibrium, where particle number can change, and kinetic equilibrium, where particle number won't change, but you can maintain temperature between fluids. And the difference between those is important and will come up later. So, good. That's everything I need you to know about cosmology for the purposes of this lecture. I hope you have taken a moment and just internalized it. Good. Now we will use it. Not right away, but we will be using it. Okay. So, what I'd like to do in this lecture is I'd like to talk about what it is that we start off by talking about what it is that we know about dark matter, what it is we don't know about dark matter. The way you might think about this is if you had the title of the lecture something like, so let's suppose you want to build a model of dark matter. Okay? Where do you start? What do you need to know? What are you constrained by? And the thing that I would emphasize is that right now we really know lots of negatives, so that when you're writing constraints, when you're writing down models of dark matter, you're trying to make sure that certain processes are less than something, that lifetimes are longer than something, and so on and so forth. We know lots and lots of negatives about dark matter. We know very little in the way of positives about dark matter. Okay? So you're usually just trying to avoid constraints. The second point that I want to make is that we know absolutely nothing at the moment about what dark matter is. I want to really emphasize this. If you think about this, if you go back in time, the way people have thought about dark matter has really evolved quite a bit. If you go back to the 30s, before then, people would have thought dark matter was a silly idea. Like, why is there dark matter? We see all the matter. You know, sure, there's some stuff that's not luminous, but, you know, there's no need for dark matter. And then they started seeing gravitationally that there's evidence for dark matter, but they assumed that it's, you know, ordinary atoms and gas. And then after more data come in, then it's clear that it can't be ordinary atoms and gas. Maybe it's neutrinos. And then everybody's on the neutrino bandwagon, and everybody considers everything else to be exotic. And then after a while, it seems like neutrinos don't work, but everybody's very into supersymmetry. And you'll read papers where dark matter and neutralino are used synonymously. And now we're moving past that. But the point is that at every single point in time in our history, people have had a lot of confidence in what the most likely model of dark matter was. And every single time we've had a lot of confidence, we've ended up not being right. So people like me or, you know, Nate or Mike will get up and say to you, you know, here is this great model of dark matter. You should be incredibly skeptical of us because it's really just what we're familiar with, what we get used to. Biases quite a bit. Not you, Michael. It's all good. So, all I mean to say is that our ideas of what dark matter are change. And so, if somebody says to you, oh, dark matter doesn't really act like that, that would be very unusual for dark matter, you should be very skeptical of that. Who's to say what dark matter should act like? Be very, very skeptical of any sort of positive statement of what ordinary dark matter looks like. So, what is the evidence we have for dark matter? These are the things that you need to absolutely satisfy. First, Zwicky and the coma cluster. In the 30s, Zwicky observed the coma cluster. So for those of you who do not do cosmology, this is a cluster. These are all galaxies, and they fly around in all sorts of random directions. So you can go and you can look at this cluster, and you can measure how fast these galaxies are moving. You can assume that the system is virialized, so that is that the characteristic kinetic energy of any one of these galaxies should be comparable to its potential. And you can then use this to infer the total mass of the system by how fast these galaxies are moving, right? So if they're moving very, very fast, there has to be a lot of matter. If they're moving very slowly, there has to be very little matter. And from this, the inference was that you needed 10 times more than observed, more than the luminous matter. And even that was an underestimate. So, right, you go out, you count the galaxies, you know how much a star weighs because we have a star. You look at how luminous these galaxies are, you figure out how many stars they need. That tells you how much mass is in the luminous matter, in the stellar matter. That tells you how much mass you see. You calculate their motions. That tells you how much mass there is, and you compare the two. You find out you need a lot more mass than you observe. Now, that's not a crisis, of course, because there's lots of mass that we don't see, right? You don't really see planets. You don't see very cold gas. Back then, they didn't see hot gas. There are all sorts of things that you cannot see. But that's the first step where you actually need some matter which is not luminous. The game change comes in the 70s, where Vera Rubin and collaborators looked at rotation curves of galaxies. So here is your galaxy. Okay? It's a spiral galaxy, it's rotating, and you can measure the velocities at these points, and then you can find distant systems here and measure their velocities as well. So everything is orbiting around some central potential, and you can make a plot. Now, if all the mass is concentrated with the light, then as you move farther and farther away, Newton's law tells you that the force should drop like 1 over r squared, and if the force is dropping, then of course the acceleration is dropping, and so the v squared over r is dropping. So you expect a curve that looks something like this. So this is expected. And what was observed was more like this. And importantly, that includes these objects which are way out here. So what that's telling you is that the only way that you can have these objects continuing to rotate with these velocities is if there's a lot of mass around here that you cannot see. And so that's the first really strong evidence for dark matter as we think of it now. Because if, unlike in Zwicky's case, where it could have been matter distributed more or less ordinarily, here, this really can't act like stars. It can't just be unexploded stars or planets or anything like this. You have a type of matter which is really distributed in a way which is fundamentally different from how the observed luminous matter is distributed. So, as time has gone on, we've now gotten tremendous new pieces of data. Let me emphasize 3 more. One of them is from lensing. So, as we said before, you have your galaxy cluster. Okay? And you have your observer over here. And then you can have some distant galaxy. And the light from that distant galaxy lens can be bent as it comes around the cluster in between you and the galaxy. And that lensing can be a strong lens where you actually really bend things coming through different paths, or it can be something where you simply distort the image slightly and you need to infer its presence statistically. But lensing has become a very, very powerful tool for measuring the presence of mass between us and some distant object. So you can use this as a means to make measurements of the masses of individual galaxy clusters. And of course, the most famous example of this is the bullet cluster. The bullet cluster, where you started with 2 clusters. Clusters tend to have a lot of hot X-ray emitting gas in their centers, and we believe that the dominant amount of mass is in the form of those hot X-ray emitting baryons. So you started with one cluster coming this way and one cluster coming this way, and what happens is that the gas collided, and when the gas collided, the gas slowed down, but the mass continued to move on. So you have some amount of mass that you can infer gravitationally, and then some mass that you can infer from its X-ray emission. They collide, and the X-ray gets slowed down by the collision, whereas the overall mass continues on. Now, of course, we did not observe this process. This process happened over an extremely long time scale. Really, we just observed this, where we see these 2 X-ray emitting spots, and we do a lensing map to infer the presence of dark matter. But the critical thing from this is that it is the first example of a system where the center of mass and the center of baryons have actually been separated from each other. And that's a very strong constraint on models of explaining dark matter through things like modified dynamics, because you need to have a system that can actually separate the dark matter from the luminous matter. Next is this growth of structure. So as we said before, the universe is full of these density perturbations, delta rho over rho. And those perturbations should grow. And you start with a small perturbation, and it should get larger and larger and larger, and eventually it becomes the galaxy that you observe today, or something like that. And you can do this in a variety of ways. You can study the growth of structure in a variety of ways. One of them is with the CMB. Which, of course, has this famous plot. The other is by looking at the dimensionless power spectrum, which is something like delta rho over rho squared. And what you can do is you're essentially going out and you're making measurements of the universe, counting galaxies, and asking questions like, in a volume of the universe, if I look at the universe on, say, gigaparsec scales, how large is delta rho over rho? And as I move to smaller and smaller scales, how large is delta rho over rho? And what you see is that this increases and then turns over for reasons that are related to matter radiation equality. But this is a prediction of your dark matter model or your cosmology, because you start off with some primordial perturbations, they grow in some fashion, you go out, you compare to what you observe in the universe, and you make a quantitative comparison. This is most pronounced in the context of the CMB, and the reason for this was this point that was brought up earlier. So let's take a step back. As we said, overdensities in the universe, when you enter matter domination, grow proportional to the scale factor. Okay, so they grow proportional to A. Whereas in radiation domination, they grow proportional to log of A. So it's a very, 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 very slow growth of these perturbations, and then matter domination happens and they start growing very rapidly. But that's for dark matter. Dark matter is cold and collisionless, so if it's got a gravitational potential, it just likes to fall into it. Baryons are very different. In the early universe, baryons are interacting with the photon path, right? Protons and electrons have electric charge. So when you try to force protons and electrons into an overdensity, they push back. They have pressure. So, since we have matter radiation equality is at approximately 1 eV, and recombination is approximately 0.3 eV, you have this period of time in the universe where perturbations in dark matter can grow, but perturbations in baryons cannot. And so if the universe were actually just some exotic form of protons and electrons, its form would not be able to start growing until all that matter had combined into hydrogen. So structure would not have started growing in the universe until 0.3 eV, and these plots would be very, very inconsistent with the data. Okay. So this is something that has to be very, very importantly taken into account in thinking about dark matter models, is that at 1 eV, it really was already acting like dark matter. Okay? It was cold, collisionless matter that was forming into overdensities. If it was made out of protons and electrons, that could not have started happening until significantly later. Now, I draw this plot here, and it's not so important for you to understand exactly what I'm drawing. Like I said, this is a measure of overdensity as a function of scale. So at very, very large distances in the universe where there hasn't been a lot of time for these things to grow, there's a certain amount of overdensities. As you go to smaller and smaller scales, the average overdensity gets larger and larger and larger until you get to around 100 megaparsecs. At around 100 megaparsecs, then normalized in this way, that turns over. And this is around 10 megaparsecs is the distance scale at which delta rho over rho is approximately 1. That's sort of where the universe begins to become nonlinear. So in this regime here, the universe is very, very nicely linear, and things can be calculated either with fairly straightforward tools or with more sophisticated tools, depending on your precision. As you go to distances which are smaller than 10 megaparsecs, then it becomes harder and harder and harder to calculate these things. So when you get down into this region of the universe, where people actually don't use galaxy surveys, but people use Lyman alpha systems to measure the average overdensities, it becomes very nonlinear, and it becomes very hard to constrain. So we know that dark matter was clustering like dark matter at a temperature of 1 eV, but it actually, because this looks like it was working even better than that, it was actually clustering well prior to 1 eV. And I'll talk about that in a little bit. The last constraint that tells us that dark matter is actually out there isn't really a constraint on the existence of dark matter, but a constraint on the absence of additional baryonic matter, which is, of course, BBN, Big Bang nucleosynthesis. So you can go out and measure the abundances of lithium, helium, hydrogen, deuterium, and you can go and you can take your favorite code and you can run it and see how much an ordinary universe would have predicted for how much of those same elements there should be. And all this is dictated by a single number, which is the baryon to photon ratio. And we now know that the baryon to photon ratio is about 6 times 10 to the minus 9. If it had been much larger than that or much smaller than that, then the abundances that we would have gotten are very, very different. But importantly, we now have measured this baryon-to-photon ratio independently from the CMB. And if you take this, this turns out to tell you that omega baryon, which is the energy density in the baryons divided by the total energy density in the universe, is approximately 0.04. Okay. So if there is dark matter, it should be something other than protons, neutrons, electrons, and so forth. Questions about this? Yes. Yes. So the question is, does 0.4, this one, yeah, this one, constrain the dark matter self-coupling? It does. I'll come to that in a second. It's probably not the biggest constraint on that usually, but this can all be understood by the fact that dark matter is a non-interacting fluid. So as you turn on interactions, then you start leading to deviations from this. And there's actually a fairly recent paper by Siracine and collaborators, and I can find that and tell you the precise things where they put constraints on the size of dark matter interaction precisely from looking for those sorts of dark acoustic oscillations. And they find that there's a constraint that whatever Fermi constant, if you will, dark matter Fermi constant, should have a scale which is something larger than about MeV-ish denominator. So it's like smaller than like 1 over MeV squared approximately, except for they do find that there's a particular point in parameter space where maybe the fit is better than if you have none at all. But if it's better if you want to go there, we'd go there offline rather than me saying it here. Okay. So that's all the evidence there is for dark matter. Not all the evidence, but that's the dominant set of evidence for dark matter. The reason why I wanted to point that all out is that all these pieces of data are from very, very different environments. Right? The CMB is from when the universe is about 300,000 years old, when the universe has a temperature of about 0.3 eV, and perturbations are very, very linear. Galaxies in Lyman alpha systems go from both linear to nonlinear regime, but involve the integrated properties of the universe over the history of the universe. Lensing is a totally different technique that allows you to measure the mass of objects out there. Rotation curves are on a size that's smaller than lenses. And of course, BBN is a completely orthogonal measurement from all of these about what types of matter there are in the universe. And the reason why it's worth noting that all is that dark matter is not a single piece of data, right? And if you go out and you talk to your average person on the street, they will probably point to rotation curves as being the best piece of evidence for dark matter. But in reality, there's evidence for dark matter all throughout the history of the universe from a variety of experimentally independent techniques, and they all point to the same idea that there is a significant amount of dark matter in the universe, about 6 times more abundant than ordinary matter. Okay? So at this point, it's worth noting that this is the conservative option, right? It's not the conservative option to say, oh, well, maybe Newtonian dynamics is modified. Maybe Newtonian dynamics is modified. Maybe that is the explanation. But that's not the conservative option. The conservative option is there's just some stuff that you can't see, and you want to find out what it is. Questions? Okay. So that's the evidence for dark matter. So what do we know about its properties? What are the constraints on it? So, like I said before, it's mostly negative. At 0th order, we know that it's massive, i.e. that it actually has some sort of energy to it, and that its mass is like mass, not like radiation, so that it has an equation of state which is very close to 0. So it's nearly pressureless. There is an idea which is the in cosmology that people like to talk about, which is the co-moving horizon size, which is to say that you can take a scale today and ask what that equivalent scale was in the early universe, right? So you can talk about the megaparsec scale at any time in the early universe, even though it was much smaller then. And so what you can ask is, as I go down to the smaller and smaller and smaller scales where I've observed dark matter perturbations, what's the smallest scale that I've currently observed that, and how big was the universe when that was the entire universe, right? So I can say, go back in time and say, I see galaxies now that are, say, 100 kiloparsecs in size. How far back do I have to go in the universe when the entire horizon of the universe was that, okay, even though it was contracted? And the answer to that is that the objects that we observe came inside the horizon. So this is what you say. They came inside the horizon. These modes came inside the horizon at temperatures of about keV. So if you go back to temperatures higher than a keV, the horizon size was very small, and the parts of the universe that were inside those patches of the universe are smaller than the scales that we can currently test dark matter on. When the universe was about a keV, you had regions of the universe that have now turned into structures that we can observe. Therefore, starting at about a keV, dark matter better have been acting like dark matter. So when I say that dark matter is massive and approximately pressureless, I mean that it is massive and approximately pressureless today, and that it had better been approximately pressureless ever since keV. Prior to a keV, I can't actually say very much about how dark matter was.
So what sizes are those, like in parsecs?
In parsecs, this ends up being, it's much smaller than megaparsecs. This ends up being about a kiloparsec.
How true is it that dark matter is really cold? I mean, there is some research on warm dark matter, but hot dark matter.
Well, we can talk about that. We can talk about that now. So all dark matter is cold. All dark matter that explains the structures that we observe today is cold today. When people make a distinction between hot dark matter, warm dark matter, and cold dark matter, it's actually a little ambiguous what that means, but typically it means what the characteristics of that dark matter were within experimental ranges of validity or when it was formed or something like that. So, for instance, take the extreme example of neutrino dark matter, which is the sort of quintessential hot dark matter model. If you have a neutrino which is 0.1 eV in mass, let's just say, which is approximately okay with roughly the same as what you want for the long baseline experiments, then the neutrino became non-relativistic at z of approximately 100 or so. Okay? So, yes, it's hot dark matter in that when it was around earlier, it was hot and it free streamed and it smoothed things out, but well before now it became cold. So, what I'm saying when I say that it's massive and cold, I mean that the dark matter is massive and cold today, and it has been massive and cold ever since temperatures of a keV and later. Warm dark matter is then characterized as being right on the cusp, essentially, where it had temperatures at keV that were around a keV, and so right where we're starting to lose the ability to discern these structures, it was starting to smooth these things out. And that's useful then for trying to change structures that we observe in galaxies, deplete some subhalos, smooth out some cusps. But all dark matter, that is the dark matter, so if you assume that there's only one type of dark matter, all dark matter models that explain the dark matter are cold today and have been cold since about keV. So the next thing is that dark matter, these are all zeroth order things, should be neutral. Neutral, I mean electrically neutral. And so let me just talk about two different possibilities for that and the constraints on them. So the simplest possibility is you can imagine that dark matter actually carried some electric charge, And if it carries some electric charge, then in the early universe, it would actually be tightly coupled to the photon and baryon plasma as well. So as we said, baryons can't start growing their density perturbations until recombination because they're tightly coupled to the photon bath. And if dark matter had an electric charge, it would also be tightly coupled to that same photon bath, and it would not be able to grow its perturbations either. So you need the charge to be small enough so that dark matter is not tightly coupled. And there's a paper that's a little confusing to read just because it was written a long time ago and things have not dramatically changed because this is a qualitative statement. By Dubovsky, Gorbanov, and Rubtsov from way back in ancient history, back before there were dots and archive numbers. And they basically found that if you make a plot of charge and mass, here's 10 to the 10 eV, here's 10 to the 14 eV, and here's 10 to the minus 6 of the electron charge, and here's 10 to the minus 5 of the electron charge, that something like that region is ruled out. The reason why I've drawn this plot in this funny way is that there's actually in their plot a lot of additional information in here that's not really relevant for us anymore. But you can see that even for very, very small couplings, very, very small charges, dark matter becomes tightly coupled to the photon bath. If you have a lighter dark matter particle, it becomes tightly coupled more easily, and thus gets ruled out from that. The other thing, in terms of charged dark matter that I just want to comment on, is that you might have the idea of, because lots of people have had this idea, is, well, maybe the final particle is not charged, but maybe there's a very, very, very massive thing like a proton, but it weighs like a TeV, and it has an electric charge, and it binds together with something else that's like a very, very massive electron, and they make a neutral object even though the constituents are charged. Okay? But let's suppose they bind together from electromagnetism, not from like strong interactions, not like neutrons, but like you really have a TeV mass proton and a TeV mass electron, and they bind together. That is also ruled out from something called heavy hydrogen searches. So you can go out and you can get water, which is made with a lot of hydrogen, and you can look at it to see if any of the water molecules contain within them heavy hydrogen, because if you have these TeV mass protons and TeV mass electrons, occasionally they will bind with an ordinary electron, and that ordinary electron will chemically interact just like hydrogen, and it will form water and such things. And so the constraints on this is that the abundance of this, so the fraction of ordinary hydrogen, which is in the form of heavy hydrogen, is less than about 4 times 10 to the minus 14 for something that's sort of heavier than ordinary hydrogen and less than about a TeV. And I just bring that up not because this is the model constraint that you're going to most run into, but just to emphasize that there are, when you start thinking about any specific model, oftentimes these very, very precise studies, these precision searches that have gone on that can constrain what you're talking about. Yeah?
Excuse me, could it have color charge? I mean, like colorless bound states?
So literally color charged?
Huh?
Literally color charged.
Literally, yes, but of course, colorless bound states.
Yeah, so there's a type of dark matter that's called quirky dark matter that functions like this. That is more or less fine as long as you understand its thermal history well. And colored particles have a very confusing thermal history. But as long as the object itself combines to a neutral object that cannot bind with an electron, this is fine. You have to make sure that the object that you're talking about has its lowest energy state such that it is actually electrically neutral and doesn't have approximately degenerate things like that. But yeah.
That could be it's not excluded by some like all the epoch where the constituents were separated. It's not completely excluded.
The cosmology, I'll just say the cosmology of it depends on how massive your particle is. Depends on if your particle is very, very heavy, then it largely looks very wimpish. If you're trying to make something lighter, then the cosmology becomes much more complicated.
Wouldn't that also affect the QCD beta function running? Then you have new particles.
Yeah.
Light, so that's good.
Yeah, but I'm assuming that we're going to put it at a mass scale where it's not going to mess with that. But yeah.
So by light you mean still.
Yeah, I'd have to think about what the actual limits are on how light that can be. Yeah.
Just remedial question. How do I read that? Is that a limit for particle numbers?
That's the abundance. That's the fraction of hydrogen which is in the form of super heavy hydrogen.
And for the mass in that?
For this mass range, yeah, that's right. If it's lighter than this, then they're not very good at finding it. So, right. Okay. So dark matter is neutral. It is cold. And it is non-interacting. So when dark matter is non-interacting, what does that mean? What that means is that at current levels of simulations, to leading order, dark matter that does not interact at all is in good agreement with the data. And we can have arguments about that, about cores and cusps and dwarf galaxies and things like that. But at leading order, a dark matter particle that has 0 interactions is fine. Therefore, when you turn on interactions, you basically start running into problems, if not immediately, then very, very quickly on the order of magnitude type plots. So the leading analysis that you do is just ask the question, how large do I have to be before I start getting any sorts of interaction? So you pick your favorite system, you find the number density in that system, you find the velocity of the particles in that system, you ask how long that system has been around. So for instance, you take the Milky Way galaxy, you measure how much dark matter is in it, you look at how fast things are moving, about 300 kilometers per second, how long has it been around, about as long as the age of the universe, and you set that equal to 1 to get a cross-section limit. And the cross-section limit that you get from lots and lots and lots of different of different systems is this, that the cross-section divided by 10 to the minus 24 centimeters squared is less than the mass divided by TeV. The way people like to talk about this is that the cross-section per mass is less than about 1 centimeter squared per gram. That's how astronomers talk about it. These numbers end up being about the same. And it's actually it's quite remarkable that you end up with very, very similar limits from many, many systems, dwarf galaxies, clusters of galaxies. The one that people will point to the most is if you look at the bullet cluster, when these two clusters collided with each other, if there had been a large amount of scattering, then the dark matter halos would have slowed down as well, and that ends up with a limit which is about a factor of 2 stronger than this. If you convert this into just natural units, this ends up being about 100 MeV to the minus 3. So I'll just make a note of that now because that will come up later as a relevant scale. The other thing that I will say is that these different systems have different velocities. So dwarf galaxies tend to be very slow, clusters tend to be very fast, and so you come and you have a hard limit like this from the bullet cluster where particles are moving at a few thousand kilometers per second. Those limits would not necessarily be relevant inside of the Milky Way. So when people say that's the limit on dark matter cross-sections, that's really the limit on dark matter cross-sections in that system. And if the dark matter has a velocity dependence to its interaction, then those can be easily abated. Two last things. One about force. you might ask whether dark matter can have an additional long-range force. And there is a paper by Kesden and Kamienkowski. I actually didn't write down the year. So the idea is, what if dark matter had interactions that bound it inside of the galaxy that were different from ordinary gravity? And they found that the strength that they called B should be less than 0.2, which is to say that the coupling of dark matter to a scalar should be less than 0.2 of gravity. And the limits come from the fact that if you look at dwarf galaxies that are orbiting around our galaxy, those dwarf galaxies have dark matter in them and baryons. And if the dark matter and the baryons had different types of interactions, then they would actually orbit at different rates. You'd have an equivalence principle violation, and you'd get a separation of the dark matter from the baryons, and you'd lead to a stream of baryons falling out of the dark matter halo. The absence of those led to this limit. Now, I don't know that I would necessarily hold this number completely rigorously, but certainly order 1 deviations to gravity can lead to changes on the galactic scales. And the last constraint is that they should be stable, right? So dark matter, people talk about cold, collisionless dark matter. It should be neutral, it should be cold, it should be dark, and it should be here. So it has to be stable, but how stable? The most recent analysis I know of this is in this paper, where they looked at what happens if dark matter is decaying into invisible particles. If dark matter decays into electrons or photons or protons, there are all sorts of limits on that. But if dark matter just decayed into something invisible, which meant that as the universe was expanding, dark matter was actually diluting a little bit more rapidly than it should have been, then you can see those effects on cosmology. And they put a limit, which is that the fraction of decaying cold dark matter times the rate of decaying cold dark matter should be less than 0.086 times age of universe. So if dark matter is decaying, it better have a lifetime which is longer than about 10 times the age of the universe. Otherwise, it will start having cosmological problems. Okay? But at this set of requirements, we're pretty much ready to start building models of dark matter. If dark matter has relatively small interactions, relatively long-lived, neutral, and cold, at least since KeV, that's going to be an acceptable model of dark matter as long as you get the abundance right. So I'm going to stop there, and we will pick up tomorrow with models of dark matter. And I left some time for questions, and I can also take questions after. Questions? Yes.